Hello, everybody. Welcome to my presentation. I am Antoine Hémery. I am a staff software engineer at Algolia, and I've been working in the company for 7 years. I am working in the engines team, which is responsible of developing and running in production Algolia search engines. And when I'm not debugging encryption or other information retrieval problem, I'm into gardening, cooking, and sports, and currently I'm really into French boxing. All right, so how is this problem started? It started with a problematic customer. So as I've said, I am running the engines in production, so I'm on call. So we had this very particular customer, which is Snell & Co. Maybe some of you work here. And we had a lot of incidents with them. So they woke me up at night a bit. We had overloaded server with them, creating outage. We had scaling and latency issues. So we had to write a lot of post-incident review. So you can see a picture of me debugging one of their problems. So in short, it was every ops people nightmare. Why it was problematic? So we can compare Snell & Co. to one of our other customers. So they are a typical e-commerce use case. So they have 6,000 requests per second on their server, but to handle their load, we needed 180 machines. But on the other side, we have Rabbit & Co., which is another e-commerce customer with the same use case as Snell & Co. They have way more traffic. They have 45,000 requests per second, but for them, we needed only 70 machines to handle the load. So between the two customers, we have a scaling factor of 20. It's a lot. And the problem with Snell & Co. is that to provide them a good service level, we needed to pay a lot of money to the providers, so almost $500,000 a year. So that's not acceptable. We need to do something. So the problem, we have two customers with the same use case, using the same machines, but we have a big scaling factor with them. So what's wrong? So as good engineers, to understand the problem, what we've done was to look at metrics, vitals. So the first one, basic CPU. It was okay. Then we looked at the RAM and the memory usage. Same, it was okay, nothing wrong. We then started to look at I/O metrics and further throughput. Same, we were not hitting any limits or thresholds. It was okay. Then we started to look at more business-oriented metrics, and one which is important to us, the index load time. So what is it? So it's the time to load a new index from disk. So our customer, when they send update to Algolia to update their indices, this index needs to be loaded from disk to memory. And this can take time, it's not instant. So for example, if you have a query time of 200 milliseconds and the load time of 100 milliseconds to load the index from disk to memory, the first query hitting the new index, the refreshed index, it will take 300 milliseconds because we need to first load and then execute the query. So for Snell & Co., they have a very particular indexing pattern because they index a lot. So they have 4 loads per second per machine with a median load time of 300 milliseconds. So that means that for half of their load time took more than 300 milliseconds. So that's a lot. So to compensate this, we scaled out horizontally the machines. So now that we had an idea of the problem, we could reproduce it on a test instance. To understand how to reproduce, we need a good overview of the architecture of the search engine. So you can see the search engine has two separated subsystems. The first one is the indexing subsystem. How does it work? So when a customer sends an update to Algolia, it goes through the indexing API. This update is then enqueued to the indexing queue. Then we have one to many builders pulling the jobs from the indexing queue. And when the builders are done writing the index, they send them to the remote storage and are available to be pulled by other services. That's where comes the search subsystem, the second one, which is responsible of pulling the indices from the remote storage to make them available for search to one to many searching units and then it's available for the end user through the search API to search publicly the indices. So maybe you have an idea with this architecture how we could put pressure on the search subsystem with the indexing subsystem. In retrospective, that's kind of easy. So what we did was to have many indexers targeting one searcher. So we have, let's say, 4 builders on the indexing subsystem and building many indices for one searching unit. So what was happening is that the builder are writing lots of indices, sending them to the remote storage, and then we have one searcher pulling all those indices locally on their disk. So that created a lot of pressure on the disk, and that reproduced the exaptame pattern we saw with Snell and Co. So now that we have a reproducible scenario, we can play with hypotheses to validate them. So we had a dozen of hypotheses, but today we focus on the ones that led to a breakthrough, which was comparing Azure to AWS. So why is that? It's because Snell and Co, they are running on Azure, and Rabbit and Co, let's say they are running on AWS. So they have, as we saw before, similar use case. So that's why we wanted to test the two providers. So maybe something's different between them. So in theory, Azure, the disk we have on Azure are way more performant than the one we have on AWS. They have more high OPS, they have better throughput. They are both encrypted at rest because at Algolia we encrypt all the data at rest because it's security compliance. On Azure, it's a local SSD, whereas on AWS, it's a EBS GP3 remote disk. So you would expect Azure to perform better because it's a local disk, it has better spec. That's not what happened. With the reproducible scenario, what we saw it was better performing for use case. So 10 milliseconds average load time compared to 500 millisecond average load time for Azure. So something's wrong. To understand the difference between the two, we need to know a bit more about Cloud I/O. So big picture of Cloud I/O. In the cloud, you have two kinds of storage and disk you can use. The first one is called a local or ephemeral storage. So a local or ephemeral storage is a storage that is physically on the VM host. So it's like the disk you have on your laptop, for example, but it's shared between multiple VMs. It's faster because it's local, but it has the disadvantage of having the data disappear when the VM restarts. Then you have another kind of storage, which is called persistent storage. So this one, you can see them as a big servers of disk, which is called a storage area network, a SAN, which is linked through a network link to the VM host. So since it's not local like a local storage, it's in theory less performance than a local storage. But the advantage of a SAN, of a storage area network, is that when your VM restarts, you can still benefit from the data that was stored on the disk because you can reattach to the disk because it's not lost. But in our case with Azure, we had a local storage. So how does it work, a local storage? So you have the hypervisor hardware, so the big machine hosting many VMs. So it has a big disk that is shared between many VMs. To schedule all the IOs and operation on those disks, there is an hypervisor software. So in case of Azure, it's Microsoft Hyper-V. And then on top of that, we have the guest VM. So in our case, Algolia, the engines. So when Algolia does an IO, it goes through the hypervisor software, so Hyper-V, before going to the hypervisor IO. We encrypt data at rest. And to do that, on Azure, we use the encryption at host module provided by Microsoft. So what it means is that all I/O coming from the guest VM was going through the hypervisor software. It was encrypting the data and sending it to the local storage. Now that we knew we need to profile the disk, we need a metric to use to know where it's slow, why is it slow. So the first one people would use is I/O wait. I/O wait is a percentage of CPU time waiting for an I/O. It's a standard metric, but be careful, it's noisy, it can be misleading. This metric was relevant for spinner disks, so the old kind of disk, And it's not relevant for SSD because you have heavily parallelized I/O operations, whereas on spinner disk they are mostly sequential. So that's why I/O wait it's not accurate for SSD. So using it was not good for our use case. There is another one which is I/O state await, and not the difference. This one is the average latency of an I/O request. So it's a direct disk metric. Same, it's not 100% accurate for an SSD, but in our case, it was enough. It gave enough signal to debug. So what we've seen with this metric, when we run the reproducible test on Azure, we have 15 millisecond I/O state await on the host, whereas on AWS it's 2 milliseconds. So something's weird. So what could be different with Hyper-V? With our investigation, it turned out that the encryption at host feature was responsible of the latency. So to work around that, we could disable encryption. So it's not compliant, we can't do that. But for a test, it gives a theoretical guideline. So we can use that for the test, but not for production. And for production, what we could do is to encrypt the VM ourselves. Because Linux VM, we can encrypt them with the encrypt, so we could do that. So let's test those two workarounds. We did the test, and you can see that we have way better I/O state await metrics. So without encryption, so this we have 3 ms on average. With Linux encryption, we have 5 ms. So it's way better than with the encryption associated feature. So that confirmed the encryption associated feature was a problem. Now we have better performance. It's not as good as AWS, but maybe we can do something with Linux kernel to improve the default encryption performance. And that's good news because we were not alone in that problem. When we did our research, our state of the art, we found this excellent blog post from Cloudflare, which is called Spinning Up Linux Disk Encryption. So in short, the decrypt logic in Linux was written a long time ago when spinner disks were still the default. And to optimize the encryption for spinner disk, all the I/O were going through work queues to before being set to the device and to the cryptd API. And it turns out that with SSD, which has heavily parallelized I/O operations, this is not efficient. So what Cloudflare proposed in their patch to the kernel was to disable those work queue for read and write operation. And in their blog post, they noticed very good performance improvement for their use case. So we thought, let's test that. We did. And we got really, really good performance. So on average, with optimal Linux encryption, we have below 1 millisecond of I/O state await, which is very good. And compared to the US, it was even better. So it's good news. So we found the problem. That's great. But now how do we solve it at scale? Because we are running on Azure and encrypting the Linux VM ourselves would be tedious in production. So we need to get in touch with Microsoft to solve that. So we got in touch with Azure support with all the data we had. So we opened a ticket to Azure support, and the collaboration began, and it took many calls and emails and different meetings with their team to reproduce and troubleshoot this issue. So we had call with them, testing different VMs with different FIO commands to understand what was going on. At some point after some months, we got this good news from the team. Hello, Algolia. We have some important information regarding the ephemeral disk encryption performance issue to share with you coming from our engineering team. So that's good. What was the problem? So it turned out that Azure VM v5 and above automatically encrypt their temporary disk at the hardware level. So what does that mean? If we circle back to the picture of how I/O works in Azure. So we were using the encryption at host module, which was encrypting at the software level, hypervisor level. But if you use a V5 machine, the local storage, so the hardware, is automatically encrypting your data. So that means that in our case, we were double encrypting the data, hence the title of the talk. And that was bad for the performance, very bad. So now it's solved for good, and for all of you actually, because if you were using encryption at host on a V5 machine, you will have you would have the same performance, the bad performance we had. So it's gonna help a lot of people. So the next step, what we've done, since we have V5 machine, we could disable this encryption at host feature and observe the efficiency gain. And that's what we did. So for Snell & Co., our dear customer, we went from 40 VMs on average to 3 VM. So the cost problem is solved, the latency problem is solved. It's good. So the takeaways of this scenario. Scientific method, it works. So don't hesitate to formulate hypotheses and then design a confirmation experiment. And then you can iterate on this experiment to confirm and dismiss your hypothesis and move forward into your problem and narrow it down. The other one is don't give up on your provider support. I know sometimes you can feel it's time consuming because you need to write emails, write reproducible command and etc. and have meetings, but they have access to information you don't have, and you will speak with their engineer which are knowledgeable on all those topics, so you will also learn a lot of information. And if you wanna know more about how we reproduce all the FIO command, everything, and all the technical details, you can check our blog post when we wrote everything down. Thank you for listening to my talk.